What's up, peoples? This video is to help you with strategies when it is a two-object problem and the objects will end up in the same place in the same time. And that's the key, is that it's same place, same time. That's either they pass each other, they collide, something like that. But the end of the story is that they will be in the same location at the same moment. Okay, and of course, there is a strategy to go with each. At the moment, this is simply constant velocity, so there's not much we can do in terms of making it too challenging. But we have a car going east at 30 meters per second, and we have a car going west at 24 meters per second, and that west is just sticking out where I'm like, wait, west, that's left. I better make that velocity negative, which is magically making the screen move down there, negative. And they are initially 400 meters apart. So how do we get organized? Again, we list our variables for each, but in this case, we have to do something a little different. We want to isolate where they start and where they end. We don't want to call it delta D like we normally do. We want to have a final position and an initial position. This is what it looks like. For object A, you have the velocity of A, but instead of delta D, I'm going to put the initial position of A, the final position of A, and delta T. For object B, I'm going to do the same thing. Again, notice, I am not even putting numbers in. I'm just like, oh, this is that problem. And that would be my cat in the background, distracting me. But this is that problem where, this video will not be edited. This is the problem where they meet at the same place at the same time, so I need to be organized in that manner. This was shown in class, but I'm going to show you again how we got around doing this. We have an expression for constant velocity, which can be written a variety of ways, but we could say that distance is velocity times time. And delta D means change in position, which also means subtraction, which means final position minus initial position. So instead of writing delta D, I'm saying change in position, literally with math. And I can add this to the other side, and now I can write that the final position of an object is equal to its initial position plus the velocity it's traveling at for a certain amount of time. I knew that would happen. There we go. And that's going to be a key to solving this problem, is separating the distance into final and initial positions. So let's get to it. For car A, I know that it's going 30 meters per second to the right. I could do that. They are 400 meters apart. I'm going to call where object A starts 0, like on a number line, 0. That's its initial position. Unfortunately, I do not know the final position of A or how long it's going to travel for, but that's okay. I'm just getting organized, trying to get my puzzle pieces down so I can figure out how to put them together. Car B is traveling west at 24 meters per second, so that's going to be negative because it's going west, 24 meters per second. And it's starting 400 meters away from where car A is. If car A is at 0, then an initial position of car B will be 400 meters. All right. At the moment, it can seem like we don't have a lot of information, and we don't. We're missing 2 variables for each, and there's 4 variables, so there's no way we can solve for anything directly. However, we do know that the final position of A is equal to the final position of B, because it says where and when will they meet. They will meet. They will pass each other or collide if you're that kind of person, but we could be, let's make it safe. Let's let them pass each other. And we also have this magic expression that we derived, loose word there, derive, for final position. So I could literally say, oh, wait, I have a final position expression, and I know that they're equal, so maybe I can set the expressions equal. So what I'm going to do is I'm going to use this expression for my final position here. It says that it is the initial position, which is 0 meters, plus 30 meters per second times time. So again, I used this expression here for final position, and I just subbed in my numbers. For car B, again, I have final position equals initial position, plus velocity times time. So I'm going to write that out. Initial position is 400 meters. How do I know that? Because it's written right there. Plus velocity times time. Now we can write this as plus negative 24 meters per second times time, or minus 24 meters per second times time, whatever you're more comfortable doing. Now we also know that their final positions are equal. I've written that right here because they're going to pass each other. And now I have two expressions for final position. So guess what I'm going to do with those two expressions? If you don't know, let me know, because that's an issue. I'm going to set them equal. 0 meters plus 30 meters per second times time. Do you need to write the 0 meters? No, but I'm doing it because I'm setting the expressions equal and I'm trying to make a point. Oops, wrong color. That's going to bother me. Again, videos are not really edited. So this is 400 meters plus negative 24 meters per second times time. And now I have an expression here, an equation, if you will, where the only thing I don't know is time. That's interesting. So let's solve this puppy. All right. I am going to combine like terms. Don't let the units early on in the year bother you. It's 30 meters per second times time and 24 meters per second times time. I can combine my meters per seconds and my times, basically. So I'm going to add the 24 meters per second to the other side, and I get 54 meters per second times time equals 400 meters. And now I can solve for time. And the time it takes for this to happen is 7.41 seconds. I know this because I did the math in my head, and I am a genius. Not that I wrote this out before doing the video. All right, supposedly it takes 7.41 seconds. Now, where is this position? Well, let's check our work. What's nice about writing this out and being organized, stressing being organized, is that I have expressions here for the final positions of each object. So let's sub that time back in and calculate the final position. The final position of A is simply 0 meters plus 30 meters per second times time. That time, which we just calculated, is 7.41 seconds, giving us a final position of 222 meters. Yes, there's some decimals, but I'm only keeping the first three numbers that don't start with 0. You could stop here if you want. I mean, if you want, but I want to know if I'm right. And to do that, I'm going to solve for the final position of B, which is 400 meters plus negative 24 meters per second times the time that we found. We being me, but I feel like you're here with me. And may have also just had a cup of coffee, so sorry. And we get the final position of B is also, what? 222 meters. Hey, this is a good way to check your work. If you get the same final position, then you probably did it completely correct. So that's the strategy. Let's sum this puppy up. All right. In review, we've already done multi-object problems, but those multi-object problems, they did not meet at the same place, same time, and in that case, they traveled the same distance with different times, or same time, different distances. Excuse me. This problem in particular, these two objects are meeting at the same place, same time. It literally says, where and when will they meet? That should be screaming to you that you want to use DI and DF. You want to use initial and final position instead of delta D. That is the strategy. While some of you may see some shortcuts that could be used, I commend you on that. There are some interesting shortcuts and ways to manipulate math. But again, these problems will become more complex and in the future involve quadratics, where your shortcuts, they don't work so much. So please, trust me, I do this for a living. Use this problem-solving strategy. Be organized. Yes, it might take longer to set up, but in the end, so much easier. Just in review, we used the constant velocity expression, delta D equals velocity times time, separated the delta D to D final and D initial and then came up with an expression that the final position equals initial position plus velocity times time. And we don't know that final position. Some people get stuck there. I don't know what it is. Who cares? We know an expression for it, and maybe we could just use the expression. And since they have the same final position, we could set the two final position expressions equal to each other, and we can solve for time as shown previously. And then once you have the time, you can go back and solve for final position. I would suggest, doing at least one of them and then maybe doing a quick check on your calculator to make sure the other one matches up to make sure you did it right, but that's up to you. And that's it. I hope this video proves helpful in some way, shape, or form. And again, I got to give this 3 out of 5 stars, and I would not change a thing.